Okay guys, so today's video is going to be slightly different and it's going to be on some real life electronics. So at work I've been working on a 36 volt DC to DC converter, and the thing is it's isolated, so we're not using a charge pump to do this. So I'm going to be walking you guys through how it works, and right now we're looking at a schematic and it looks a little bit intimidating, but I'm going to walk us through it and how to interpret what it means. Okay, so as this zooms in here, we're going to be looking at where it says P3, and that's a connector where the power is going to come in, and you can see there's a common and then the 24 pin. So the 24 volt plus pin is actually going to be our 36 volts. We're just testing to see if this 24 volt will work doing 36 volts. So the key idea here is, since we're using a transformer, we don't want the core to saturate. And so when the core saturates, we basically run out of efficiency on the transformer. Okay, so basically what this is doing is the 24 volts, but what we're going to be doing is 36 volts. It's going to come in across R3, which in this case says 5K, but I changed that to 7.5K for the reason you're about to hear. So underneath that, we have a Zener Diode, and that diode is producing a 15 volt reference. So the way the Zener Diode works is it draws some current to produce that reference, and then that reference is replicated across C6 and is smoothed by C6, and then that is sent out as VCC. VCC is used as the logic, the power chip for the logic. So we're going to zoom in on that next. So don't worry about that. Let's just pay attention to that Zener Diode. I didn't want that Zener Diode drawing too much current when there was 36 volts, so I upped R3 to 7.5K just to compensate for that. So in a second we're going to zoom down and we're going to take a look at that circuit, the CD4047 chip, and then the NAND gate array that's coming up after that that's driving some of the FETs. Okay, so we're going to start to zoom down here, and that chip that you see is a chopper circuit. So basically what this is doing is going to try to create two pulses that don't overlap each other so that we can pull voltage through a transformer either one way or another. So that's how we're going to get voltage through DC voltage through a transformer. So we're going to switch it as fast as possible. So this chip here is creating that switching, and that frequency is set up by C5A and R1, the rate of which it switches. But at the top there, you can see C5B coming into that NAND gate array also. So there's a pulse coming out of that pin 2, where it says R, and that goes up into the capacitor. So the capacitor is able to get the pulse to go through because it's AC kind of as it rises up. And so when that pulse comes through, and you get a pulse from the output, the NAND gates array works through. And because, you know, a NAND gate normally comes 4 per package in a pin, and you wanted AND instead, you just connect the output to both the inputs of the next one to get an inverter. And so those are able to drive a FET because they are able to produce like 5 to 10 volts. I think they're actually able to get close to like maybe up towards the rail of like 15, but I'd say maybe they get to 12 volts on the output. They're lucky, but the switching rate is going to be limited by the gate capacities of those capacitors. So we're not using 2N7002s anymore. I didn't mean capacitors, I meant transistors, but anyway, moving on. So this chip here, you can see that VCC that came in off the Zener voltage reference is coming into there and going to A-stable mono in the trigger lines, and then minus trigger and retrig and reset are tied to ground, and then the outputs go to the NAND gates respectively. And then 13 is left floating because we don't need to do anything with that pin. That's just basically outputting a clock that it's using internally. I think it's different from the clock going out. So now we're going to go take a look at the transformer, and we just want to pay attention to the top one, the one that says T1. It's a 1-to-1 transformer, so that means the voltage coming in ideally should be the voltage going out. And so what it's doing is the FET is passing the center tap voltage, which in our case is going to be 36 volts, and it's either tying it to one side of the primary or the other side of the primary, and that's inducing a voltage on the secondary that's rectified by D1A and D1B. That is then smoothed by capacitor 1A, and then any noise picked up in that whole process of switching is smoothed a little bit by L1, the inductor there, and then C1B smooths the output of the inductor after that again, and then that would go to your load. Excuse me. So in the following video, you're going to see that I have a dynamic load, which is basically a load that changes resistance based on the voltage, or it changes current draw based on resistance that you set. So you're able to set the load however you want it. So we want to be able to produce 20 milliamps at the output, consistently. So this is designed for, well, I was modifying a 24 volt design to work for 36 volts. Okay, so what I'm about to do is turn on my isolated DC power supply, which is hooked up through a current meter so we can see how much current's being drawn, and then the output of my circuit is hooked up to this dynamic load, which is off right now, and it's set for 20 milliamps. I could turn it on or turn it off again just to show you that it works. So right now we're going to be looking at the scope. The yellow traces the current going through the transformer, which is represented by a voltage through 1 ohm resistor, and I'm moving the trace 1 over trace 2 right now to show you when the alternating pulses happen, that they're laid on top of each other so you can see that they're together at the same voltage. And they're all scaled to the same thing. So right now, I'm about to crank up the voltage on the isolated DC power supply, and we're going to see on the output of the scope that the voltage starts to go up until the point where we start getting some frequency coming out from the switching, and then we get on the yellow or the orange trace, I should say, we can see the current going into the transformer. And right now this is unloaded on the output, and so we're kind of getting some ringing, and that's because there's no dampening happening. Dampening, is that a word? I don't know. It's not happening because there's no load on the output. But you can see we're at 37.5 volts and we're drawing nearly 8 milliamps when there's no load. And we're outputting nearly 62 volts. But when I turn on the load and draw 20 milliamps, it goes right to 37.5 volts, which is what I was giving it at the input. And we're drawing 27.64 milliamps, which means it was linear. It was perfectly linear as the current was drawing. And now we can see that the current going through the transformer, this is on reference to the 24 volts, by the way. It's not on reference to ground, or on 36 volts. So that's why it's a negative pulse. And so now we can see here, we have some frequency set up, and that frequency is coming off of the chips here, which is the NAND gate. So it's actually going onto the gate of the transistor. So the output of the NAND gate. So this is what the transistor would see to be switching current. Or voltage, I guess. So you can see that there's no overlap on these pulses, and since there's no overlap, we're never going to have a case where we're trying to draw voltage to both sides of the transformer and we just saturate it and screw it up. There's 5 microseconds of delay between each of those pulses according to the scale of that oscilloscope there. So right now, this is a close-up, and right now I'm pointing at that chip there is the chopper. That one is what's driving the oscillations, and it's driven off of that stuff right there, which is all that stuff in the top circuit with the Zener Diode that set up the voltage reference. The output of that chopper circuit is moving over into the NAND gate, and this whole circuit was molested by my hands. I pulled up pad after pad on this thing, overheating it, so that's why half of it was built off the thing, because I was tired of blowing up transistors. So these leads are going to the transistors over here. So it's easier to see in this video. So those leads are going to the gates of the transistors over there, and those gates of the transistors are pushing in voltage from this alligator clip that's going into there, and that's going across a 1 ohm resistor there. So that's how I was able to measure voltage out, or not. I was able to measure the current through the transformer. Okay, so now we're looking at some bitmaps taken straight from the scope using a floppy disk. So they're the same traces, and right now we can see of the train of pulses. We're zoomed out enough to be able to see it, and you can see that ringing pronounced. And then we're about to zoom in on another screenshot, and you'll see that the time gap, the gap from the actual, that's the voltage at the transformer. That is not the gate that's not the input voltage at the gate from the NAND gate. So that's why there's not as much delay there. So then here we can see the load train. So right, that means the pulse train when there's a load on it, it's not as much ringing. And then here's the load when it's single. And then we can see that there's not as much ringing on it, and then it comes up smoother. So those are the 4 readings out from the scope in a little bit higher resolution to be seen. Okay, so coming up are some notes. So testing was performed on this board to ensure that the transformer would not saturate at 36 volts 20 milliamps. So efficiency was recorded as a function of the output power divided by the input power, and then we varied the ambient temperature from room temperature of 22 degrees C to about 90 degrees C. We hit 40 degrees C and stopped working, drawing upwards of 1 amp. Cap C7 shorted, drawing at 38 ohms, so we replaced it. Testing was going well until it we raised it to 70 degrees C, where then things became unstable, and then current draw went to 80 milliamps instead of the normal 28. We figured that the case that the core was being saturated, the theory was that it was switching too low of a frequency and that it was saturating the transformer for about 50 microseconds before switching current in the other direction. So what we did is we doubled the frequency to about 47 kilohertz, and then the unit was able to pass at 90 degrees C and didn't run into any issues. So here we can see my Excel spreadsheet where I was keeping track of my data. So the columns go temperature in degrees C, then voltage in, current in, and power in, which is calculated off of those other two values. And then we have voltage out, current out, and power out, which is calculated off the voltage and current out. And then efficiency is calculated off of the power output divided by power input. Okay, so we can see as we move down, the temperature is increasing. And then we can look at the efficiency and see that as the temperature increases, the efficiency goes down. But in the middle there, you can see that I wrote a note that says double the frequency of the chopper by changing the 470 picofarad cap to 200 picofarads. So it wasn't really doubling, but it was close enough, you know. Then R3 was changed from 499 to 7.3K to limit the current flowing into the Zener, just to make sure that we didn't blow up the Zener. But after looking at the data sheet, I saw that it can handle up to 2 amps of non-continuous reverse current. So we were probably fine, but anyway, it was probably better. It's safe to do that anyway. So these results show that this thing was able to work even at 90 degrees C, and I hit it with 100 degrees C and it was working, but it was probably at like 69-70% efficiency. So this is what I was doing at work, and I just figured I'd share with you guys. So if you guys like it, give me a thumbs up and subscribe, and it really helps me out. And I'll see you next time. Bye.